Okay, great. So let's get started. Welcome to the tutorial on interpretable machine learning for computer vision. I'm Bolei Zhou. So I'm an assistant professor at the Chinese University of Hong Kong. So today I will give you a tutorial on interpretable deep generative models for interactive AI content creation. So you may know I've been working on interpretable machine learning for quite a while. Recently, we have done many works in the areas of interpreting deep generative model with application of content creation. Because after we interpretable the concept inside the generative model, then we can control those factors to customize the output. Therefore, we can facilitate this interactive AI content creation, like put humans in the loop of creating new contents using AI models. So this talk, we will talk about many different deep generative representations, but here we will focus on the GANs, the Generative Adversarial Network. So let's take a look at the progress for image generation. The GAN was first proposed in 2014. Then over the years, there are a lot of different GAN models have been proposed. Also, in terms of image quality, you can see that image quality are greatly improved. Especially recent StyleGAN v2 and the StyleGAN ADA can synthesize realistic image in different viewpoints and for different data type under limited data amounts. Also, recent 1 years, we see another kinds of generative models, such as neural radiance fields. There is a surge of work in those areas. So we may see many work of NERF. So NERF can take dense images with camera parameters as inputs, then can learn the model, then it can synthesize the new views for the image instance. Also, early this year, we have this OpenAI DALL-E work from OpenAI that can translate a natural language sentence into an image. So here we have an example, an armchair in the shape of candles. So this model is quite amazing because you can see before this, if you Google avocado chair, you can get nothing from Google. But right now, this model can learn how to compose new concept from the previous concept in the dataset, which means this generative model already learn how to be creative. So this lecture, we will focus on the generative adversarial network, GAN. So here is a training pipeline for GANs. We have the generator that will take a random vector as input, then it will generate a fake image. Then there will be the discriminator that try to distinguish whether the input is generated by the generator or it's a real image. So through this adversarial trainings, generator and the discriminator can getting better and better. Then after converge, the generator can synthesize the realistic image. So we will focus on the generator part because this is a core for neural image generation. This generator is basically a convolutional neural network. So it will take a random vector sample from some distribution at the input, then will generate a realistic image. So if we change the input random vector, the output will also change. So another random vector as input, another output. So this neural image generation is very simple. It's also very easy to use. So input, output, you can get the realistic image without much hassle. However, for this image generation pipeline, there is no way for people to steer the generation. Sometimes users may want different outputs. For this one, user may want a different image, want an image with different lighting condition, or they may want the same image, but different views. So current pipelines doesn't support such customization or human in the loop content creation. So therefore, we want better understand the generative model and interpret the generative models with human understandable concepts. So after we identify the human understandable concept inside the interpretations, we can actually consider those concepts as some switch. Then we can turn on and turn off and control this image generation process. Then we can edit the final output. So that we can put human in the loop of this AI content creation, then human can collaborate with the AI model to create new concepts or new content we want. So that is the motivation behind interpreting the deep generative models. So here we have this deep generative representations. So let's take a look at what are the deep generative representations. So there are two kinds of representations. So the first is a convolutional neural network for this generator. So you know this is a convolutional neural network. Then there are a lot of convolution filters. So basically we can interpret those individual filters and figure out what each one is doing. We also can looking into the latent space. You know, the latent space is the beginning of this generation. So with different random vectors, the output image will be different. So this latent space actually control what kind of concept can be inside the output image. So we can also study the latent space. So here I summarize all the interpretation approach into three categories based on their supervisions. So the first category is a supervised approach, which means we can use labels and trained classifiers to prove the representation of the generator. The second approach is unsupervised approach, which means for those models, we don't have any labels or classifiers. How can we still identify the controllable dimensions of the generator? So third approach is more recent work that they try to align some language embedding with generative representations. Therefore, they can do the zero-shot interpretation without using any labels, because right now the language embedding already aligns with this generative representation. Then giving any words or sentence, it can generate the image. Then let's get into each approach. Let's first take a look at supervised approach. Use labels and trained classifiers to prove the representations of generator. So one of the earliest work for supervised approach is the scan dissection. So it's derived from our previous work for network dissection. So the basic idea of GAN dissection is to align the semantic mask with GAN feature map. You know, for this output image, we can apply some semantic segmentation network and get the semantic labels for each one of the pixel. Then we can go back into the generator and get their feature map for some units. Then we can measure the agreements between the feature map, spatial feature map with the semantic segmentation. Then we can associate label for each one of the individual units. So it turns out about 1/3 of the units have a very clear meanings with high agreement. So after we identify the semantic filters inside the generators, then we can simply treat each filters as a switch, and the user can simply interact with the output image, like to brush some regions. We can just turn down and turn off the units at those regions. Then we can add and remove some content. So here, this demo showing you this interactive content creation. So user can brush some regions and include and remove the trees, skies, and clouds, different objects. So after we have this interpretation on the individual units, then let's take a look at another part that we're looking into the latent space, because you can see that latent space is really the driven force behind all the image generation. So if we can disentangle and identify the meaningful concept inside the latent space, then we can have more controllable image generation. So here is one work that we interpret the scene generative network. So we have a network that can generate the indoor scenes. So we want to interpret the internal representations with some linear classifiers. So what we can do is that for the output image, we can apply some off-the-shelf predictors. You know, computer vision researchers or computer graphics researchers develop and release a lot of pre-trained models that can predict the attributes or semantic labels for the output image. So we just take the off-the-shelf predictors and get the labels. Then we can go back into the latent space and identify the causality relations between the latent activations and the output attributes. After that, then we can control this generation. So how does part work? Let's dive a little bit deeper into this. So starting from this latent space, we can sample a lot of random vectors. So each blue dot is a random vector we sample from some distribution. Then for each random vector, we can throw into the generator and have this image. Then we can have the synthetic image space. Then we can take some off-the-shelf predictors and predict the attributes intensity for each one of the output image. So for this one, we are looking at this indoor lighting predictions. So right now we can treat this predict label as a pseudo label for each one of the latent vectors. Then we can train a linear classifiers in the latent space to distinguish whether these latent vectors correspond to nature lighting or indoor lighting. So it turns out linear classifier can achieve more than 90% binary classification accuracy for this lighting prediction, which means in this latent space, a lot of the feature are already quite disentangled from each other. So after this, then we have the last very important step called counterfactual verification. Because the previous three steps are just doing this correlation, we just know some correlation between the latent activation and the output attributes. So right now we want to escalate the correlation into causality. Then we have this verification steps. So what we are doing is that we take this normal vector of the trained linear classifier and add this vector on top of the original latent vector, then generate a new image, and then observe how much the attribute change accordingly compared to the original synthesized image. So we only consider those attributes can be reliable, manipulate through this. So after this step, we can identify those reliable attributes manipulator. Then we can start doing this manipulation. So our manipulation is pretty simple. It's just a linear model. So after we know this boundaries, then we can have this normal vectors. So right now we just push this latent code across the boundary by just adding this boundary vector. So gradually you can see this indoor lighting attributes is intensified for this input image. So then you can see for the two images, so you can see the lamp is turned on, and also the global lighting condition is greatly improved. So here is another demo video showing you that for synthesized image, then we can push the latent codes across the boundary. Then the lamp is turned on and global lighting condition is greatly improved. So in the latent space, not only we have this indoor lighting, we can also have many other attributes. So here is another example showing you we just push the latent code across the cloudless boundaries. So right now we have 4 images. So the sky is very boring. Then we want to include some cloud insights. Then we just push the latent code across the cloudless boundary. Then this cloud just automatically grows in the sky. So this kind of linear manipulation is very simple and generalizable. So here we apply this kind of techniques to interpret the face generative models. So here we have a face generation model, then we apply this linear classifier to identify the facial attributes inside the latent space. Then we can manipulate different kinds of facial attributes such as age, gender, pose, artifact. So later on, people start improving this linear manipulation model. We have a very strong assumption. This manipulation model is just linear. So we have this latent vector W, then we just add this attribute vector on top of that. So obviously, this is not cannot capture all kinds of transformation. Then we have a recent SIGGRAPH work from some group that they develop a model called style flow that combine style GAN with flow-based conditional model. So their model is that replace the MLP with an invertible flow model conditional on the attributes. So you can see the latent space Z and the sensitive W have this nonlinear relations conditional on attributes. Therefore, they can have this feed-forward process. Then for this sample, the W, it's already contain the attributes they want. Then this model can generate the outputs correspond to the attributes. So here is a demo video showing their facial manipulation results. So basically, they can choose the attributes they want, then generate new W. Then this new W will bring those attributes to the output phase. So from previous work, you can see in the latent space, they capture all kinds of attributes. One very interesting observation is that there are some 3D structure attributes inside this latent space. So here I show you two demo videos from our previous work. So one is changing the scene view by Yang, this IGCV work. On the right is this interface scan work that we changed the face pose. So this result is very interesting because when we first train this deep generative models, the training data we have are just those individual samples. Those individual samples are downloaded from the web. So we don't have the same multiple views data for the same instance. So all the data are just independent data. Somehow, in order to synthesize the 2D image, this generative model just figure out the 3D structures of the data. Then this raises a question, very interesting question. Does 3D structure emerge from the 2D image generation? So to better extract the 3D information, so here is a very recent work from U Toronto and NVIDIA, published at the ICOR this year. So this work tried to parse the 3D information from the 2D image generator. So they use differentiable rendering for inverse graphics and interpretable 3D rendering. So their pipeline start with the samples from StyleGAN. You can sample from the StyleGAN and generate a lot of instance, like multi-view data. And then they have very quick annotations to annotate the views of different synthesized image. So after they collect a bunch of multi-view data, then they use this to train some inverse graphics network. So the diagram on the right showing you this process. So for this inverse graphics network, the input is a image. Then this output of the network will predict the mesh, light, and the texture. Then they will throw this different prediction into this differentiable graphics renders. Then they will render those components back into an image. Then back into the image, then they can construct a loss function because this renderer is differentiable. Then they can back propagation and train this inverse graphics network. So after they train this inverse graphic network, they further use this network to train a disentangling mapping network. So this mapping network is very interesting. It's more like a parameterized model for this latent vectors. The inputs is this uncontrollable dimension such as camera, mesh, textures, backgrounds. Then they will doing this convolution or connections, then will output latent codes. So this latent code will contain all the controllable dimensions, then throw into the StyleGAN. Then StyleGAN will work like a 3D neural renderers, then to render the information into this realistic image. So here I show you some rendered controllable outputs from this StyleGAN. So this work is very interesting. It combines this differentiable renderer with a neural rendering together and try to distill the controllable information using this inverse graphics network. So there are still many challenges for the supervised approach. So here I list some of the challenges I think are very important. The first one is how can we further expand the annotated dictionary size? The number of attributes we can interpret highly depends on this annotated dictionary. So some of the concept may not inside our dictionary. So how can we scale up the dictionary is the unsolved problem. The second is how to further disentangle the relevant attributes. So one observation we have is that some attributes are actually entangled with each other. Like when we change people's age, then they will intend to wear the glasses. The age is entangled with wearing glasses. So how can we do further disentanglement on this? So that's also relevant to the BIOS of the data. The third question is how to align the latent space with image region attributes, because the latent space or latent vector is just vectors. So there is no spatial relations between these latent vectors. So then, but a lot of the case, we want to control some image regions. Then how can we build this relation, spatial relation between the latent vector and the image regions is an unsolved problem. Okay, so then let's take a look at the second approach, this unsupervised approach that we try to identify the controllable dimensions of the generator without labels and classifiers. As the generative model become more and more popular, then people start adopt this model for different cases and training on different kinds of data. So here people train some models to generate cats. So also we have this generative model for cartoons. So for those kind of data, it's very difficult to have some off-the-shelf predictors. Also, it's very difficult to annotate the labels. Like for different models, we have annotate our in-house classifiers. Then the problem here is how can we still identify these steerable dimensions without the access to the predictors or without annotating the synthesized data. So here we have a CVPR work this year to look into this problem and try to develop. So we develop a closed form of factorization of the latent space in GANs. So basically, for this image generation pipeline, we're looking into the first steps. So the first step is to convert the latent vector into the first layer's activation. So between the two is actually doing some R5 transform. So for this latent code Z, there will be learned parameter A and B that are doing this R5 transform into the latent activation for the generator. So we also have this observation feature difference. After editing is actually independent of the original latent vector. Because of this linear R5 transform, so when we do this difference on this feature, intermediate feature map, then it will independent of the original latent code, which means is actually the feature difference encodes the attribute difference. So therefore, we develop some objective to maximize the variation of the difference. So to maximize the variation difference, so ideally we want this feature difference to encode all kinds of attributes. So it turns out to optimize this objective function, then more like we are doing PCA on the learned feature map. So we can have different components that controllable components align with different attributes. So based on this work, we built some interactive content creation demo. So on the left, you can see there are different sidebars. So user can just control the sidebar to change the intensity of different controllable dimensions. Then the output image will change accordingly. So this sidebar, you can see it control different attributes such as the pose, texture, and the colors of the cats. So with these methods, we can put human in loop for this AI content creation. So that will be very promising future directions. So you can see you can imagine that's not limited to image generation. It also can be extended to other like data domains such as music generation or some industrial designs. So there are a lot of space out there to facilitate this human in the loop AI content creation. So here is another work from Adobe, I think. So they developed some method called Ganspace. Basically, this method apply PCA, so the principal component analysis, to the latent space of the style GAN. So starting from the latent space, they first generate a lot of images, then they collect the feature activations, then apply the PCA in the feature activations. So it can identify some principal components for the feature activations. So after identify the feature activations, they can go back into the latent space and treat this as a regression problem to regress the latent space according to the feature activations principal component directions. So after this, they can have latent boundaries in the latent space, and they can control this image generation. So here is a demo video showing you their manipulation results. So this their discovered component dimensions. You can see these different components control different output attributes, such as the pose of the cars and zoom in and zoom out, or some geometric change, and also the type of the cars. So you can go back to watch the video, so we don't have time to go through the whole video. So here is another work from Berkeley and MIT. So they develop a method called Hessian Penalty. So as a week prior for unsupervised disentanglement. So here the first equation is this generation equation. So image will equal to the generator on the z variable z. So they first calculate the Hessian matrix. So they will calculate the first derivative on the I, then calculate the second derivative on the j. So ideally, if two attributes are disentangled from each other, so this Hessian matrix, the long diagonal elements should be 0. So the attribute should be disentangled from each other. So in that case, they rewrite these equations into some Hessian penalties in trainings. So they want to also minimize this Hessian penalty, then they can make this long diagonal elements as 0 as possible. So here is also a demo video.
What does it mean to disentangle a neural network? Let's take a look at this generative model G. Intuitively, we'd like the change in the output image caused by perturbing one input Z component to be independent of the other Z components. Mathematically, this is equivalent to saying that G has a diagonal Hessian in its input. We propose the Hessian penalty, a regularization term that penalizes off-diagonal terms in G's Hessian matrix. The Hessian penalty can be computed efficiently during training, and it takes just a few lines of code to implement. A popular dataset in image-to-image translation.
Okay, so this is a work for training regularizers to encourage better disentanglement through this training steps. So here's another work from Shi Guangshan's group. So they try to develop inductive bios of disentanglement in the generator. So rather than use previous MLP in the latent space, so they design a more parameterized latent space. So it's more like they design this inductive bios inside the generator than train these models. So after the trainings, this latent space already quite disentangled from each other, or the different dimension, disentangled dimension already can be found through this. So here I show you some results that they have this after trainings. They can identify those disentangled dimensions such as age, race, and gaze. So it's a very interesting result that introduces inductive bios of disentanglement directly in the generator. So similar work like this block GAN or hologans also try to design some inductive bios in the generator. Then this generator can learn some 3D structure or controllable switch out of box after the training. So that is also a very interesting direction to design some normal inductive bios inside these generators. Then we don't need to do this post-training interpretation. For this unsupervised approach, there are still many challenges. So here I list some of the challenges. First is how to evaluate the results. because we are doing this unsupervised discovering, so we may get some dimensions, but how can we quantify the disentanglement? How can we evaluate the degree of disentanglement is still unsolved problem. The second question is how to annotate each disentangled dimensions. We can have many disentangled dimensions. Then how can we annotate them? So right now, just through this manual annotations, we just plot them and ask human to come up with a name for the dimensions. Also, the third one is how can we better improve the disentanglement in training process? A lot of the work have been done after the training, after the interpretation, right? So, but ideally, we want to encourage improve this disentanglement during the training. Then we can have a more disentangled model out of box after this training. Lastly, let's take a look at this very recent zero-shot approach that try to align some language in branding with generative representations. So here is a very recent work from Adobe and Hubert University. That's they develop a method called the style clip that try to combine the clip embedding with StyleGAN. So their model can work with the input like this. So giving a source image and some text inputs. So we want to manipulate the source image according to the text input. So here is the output. So the output is quite amazing. You see, it creates this person without makeup, or cute cat, or change this tiger into lions, or have a different building styles for the source image. So how does this method work? So this method try to link some pre-trained model with the StyleGAN generation. So here is a pre-trained model from OpenAI. It's called Contrastive Language Image Pre-training, shorted as a CLIP. So it is a pre-trained model from 400 million image text pairs. So they download a lot of images with text from the web. Then they can train some pre-trained model. So this pre-trained model can embed the image or any given text into this joint embedding space. So after they have this CLIP joint embedding space, then they develop some optimization objective. So this objective is to try to optimize the latent code to generate some image to satisfy the conditions. So they first have the source image. So they can do this GAN inversion to invert this source latent code WS. Right now, they want to optimize the W. So this objective function have three components. So the first component is this joined embedding space. So you can see that it will try to optimize the latent code to minimize the distance in the joint embedding space. So here the T is a feature from the tag surprised. Then the GW is the image. So they want in the joint space, they want to generate the image that can minimize the distance in the joint embedding space. The second and the third terms are the regularizers. And the second one is just they don't want change the image content too much. So they want the latent code still be similar. The third regularizer is just on the identity. So they want to keep the identity of the person the same. So after the optimizations, so they can have a latent code W star, then you can synthesize the image, satisfy the conditions. So with this kind of iterative optimizations, so they can generate all kinds of very interesting images, such as makeup, curly hair, straight hair, bob cut for any given input image. So in this work, they also developed some feed-forward network and treated this as an objective function to train this feed-forward network. So in that case, they can just input image, then can do this manipulation directly without this very slow iterative optimization. So if you're interested, you can take a look at their papers or their paper. So here's another concurrent work from MIT. So from my previous group, done by David Bao and Antonio Torraba. So they also try to combine the clip with region-based StyleGAN inversion. Basically, user can just brush some regions. Then they want to like change the style of the bed and keep the other components of the image the same. They also develop some objective function. They manipulate some the latent code. Then they want to optimize the latent codes to minimize some loss function. So you can see on the right, those are the loss function. They take this clip pre-trained models and train to minimize the distance in this joint embedding space. Then they can optimize the code and generate the image. So here is another work from OpenAI. So it's a very amazing work. So this work explored the importance of the data. So you just train a massive number of data using a massive models. This model is a 12 billion parameter model trained on 250 million text image pairs download from the internet. So their image model is just like autoencoder model. So it's a improved version of the VQBAE. So the latent space of this autoencoder is become discrete. Then they can put more strong priors, more like language priors as transformers inside the latent space. Then the second step, just train autoregressive transformer to model this joint distribution of text and image tokens. So after they train on this massive number of data, then the results are quite impressive. So then giving any sentence, they can generate a very fun and creative image. So the middle one, you can see the input sentence is an illustration of a baby hedgehog in a Christmas sweater walking a dog. So you can generate a lot of variations. Also, the last one is this neon sign reads a backprop. So you can generate such amazing results. So here is a summary for this interpretation approach for deep generative models. So we have the supervised approach that use labels and trained classifiers to prove the representation. The second is unsupervised approach that identifies the controllable dimensions of the generators without using labels or classifiers. So we also have this recent zero-shot approach that try to use some language embedding with this generative representations. Then they can have more controls on the generation process. Let's then take a look at the latent space of the GANs generator. At the beginning, so we only have this DC GAN or original GAN. So starting from the Z space, the Z space is a source of the stochasticity. So we will sample from some random vector, then throw into the generator, then we will generate the image. But later on, we have more advanced models such as style GAN. So it's a style-based model. So the inputs at the beginning is just a constant vector. So the stochasticity is actually come from each layers. So there is a Z space and the W space. So Z space is they will sample some Z vector from this random distributions. Then we'll throw into this MLP some nonlinear layers that have this W space. So after this nonlinear transformation, the W space has much better coding capabilities compared to the original Z space. Then this W will throw into each layer. So each layer have their own ADA-in operations. So ADA-in operation will take some the latent codes W, then doing some transformations, then throw into each layers. Then each layer will have their own latent vectors. So after the latent vector after ADA-in, people come up with a new name called a style space or S space. And so S space become layer wise because each layer have their own ADA-in parameters. Then after this, then each layer have their own latent vectors. Then they will throw into the generator to reconstruct or to generate the image. Later, people come up with this W plus space in order to reconstruct the image or doing the scan inversion. Then after this, some people come up with some nonlinear operations on the W or W plus space, then come up with a P space and the P plus space. They have some unique properties on this. So different latent space have different functionalities. For example, this W space is known for disentangled manipulation. So most of the linear manipulation work happen in this W space. We just add this knurled attribute vectors on top of the original W vectors, then we can do this manipulation. For this GAN inversion, GAN inversion is that giving a real image. So we want to optimize the latent codes to reconstruct the input or given image. And then this W plus space is one of the most popular latent space people use for GAN inversion. Just more optimize the layer-wise codes at each dimensions, then we can reconstruct the real image. Then this involves a question, so which latent space is more disentangled? So we have the Z space, W space, S space. So to measure this disentanglement, there are a lot of recent work. So here are two work from CVPR. So one is from my group, another is from Hebrew University and Adobe. So looking into the similar problems. So they want to evaluate the disentanglement of the latent codes. So in this Xu CVPR work, so we use a reconstruction arrow to measure the disentanglement. Then we found out it is actually the S space, style space, is more disentangled compared to the original W space and the Z space. Also in this Wu CVPR work, they also show this disentanglement. S space have better disentanglement compared to the W space and Z space. So in that sense, seems if you do manipulation or some other operations in the S space, it will be more effective compared to the W space. That is also relevant to another inversion method, like people train some encoder for this style GAN generator. One weakness for style GAN is that, or the GAN model is that they don't have the inference capabilities. There is no encoder for this generator. Then people have to train some encoder afterwards. Then people need to think about which latent space to use as the median for this encoder and the generator. So there are many latent space to use. So here we have evaluation on which latent space to use for this encoder training. So we found out it is actually the S space is more effective to reconstruct the input image compared to the previous W plus work. So we show some qualitative results with the previous work, ALAE and ID invert. And we show that if you do this, train this encoder in the style space, you can have better reconstruction results. Also, the feature is also can be used in many different applications. So you can take a look at our CVPR work if you're interested to know more. So this kind of GAN inversion can be generalized to many image processing tasks. So we have some recent work to explore the applications of this GAN inversion. The GAN inversion, it just treats this generator as a generative image priors, and we can optimize the latent codes and doing this reconstruction. So we can modify this objective a little bit, then we can realize a lot of image processing applications, such as colorization, super resolution, or some masked optimization. So that it opened the doors to many image applications. Okay, so here is a summary. So you can see that we can apply a lot of different approaches to identify this interpretable dimensions or factors hidden inside the generative model. So interpreting the generative models can greatly facilitate this interactive content creation and the human AI collaborations. So if you're interested in knowing more, so you can refer to this recent survey papers on GAN inversion. So that's the end of my lecture. So thank you very much. And so I hope you can also check out other speakers for this tutorial. Thank you. Bye-bye.